Our next speaker is Aaron McCurry. And he's got his talk fired up here. So I'll let Aaron introduce himself, but Aaron is from Near Infinity Corporation, and I think he wins the prize tonight for traveling the farthest. He is coming to us from Reston, Virginia. So I'll go ahead and turn it over to you, Aaron. Thanks so much for coming.
Thank you. Good evening, everyone. Thanks for coming out. I'm going to talk about Lucene on Hadoop. A little background on me. I've been using Hadoop and working with big data for about 3 years. During that time, a lot of Lucene work, along here, doing a lot of big data processing. So I'm going to go over the definition of blur, key benefits, the architectural components, what problem it tries to solve, query capabilities, and a few of the challenges that it has overcome. So what is blur? Basically, it's just Lucene on Hadoop. It's specifically built with big data in mind, scalability, performance from the beginning, and I decided to not try to build a fresh search engine from scratch because there's so much goodness in the Lucene stack and in Hadoop itself, so why not put them together? So why should you care? Well, it's scalable. It stores all of its indexes in HDFS. It's fast. It's meant to be out of the way of the standard Lucene performance, so it's nothing magical, but it's going to perform very similarly the way Lucene would perform on a local machine. Everything is durable. If you prefer it to be durable, with write-ahead logs during incremental updates. Failover is built in. It auto-detects failover using ZooKeeper and fails over the shards that are being served on the node that went down. And any query that's capable in Lucene is capable in blur. It also has an interesting little twist that it has a sort of pseudo joining capability. We can talk about that. Data model. It's basically everything stored in tables. Rows are contained within tables. Records are contained within rows. Rows themselves are assigned to column families, and column families are really just used to group information. You're probably all familiar with the concept. Columns, they contain name-value pairs, but the interesting thing is you can put the same column, same name of the same column in the same row several times to create an array effect. So if you need multiple values in a column, you can just add it multiple times, similar to the way fields work inside Lucene.
Can I ask you a question?
Sure.
So we have got 4 other different products which kind of does similar things. So if you can touch base that why one more search product.
Are you referring to Elasticsearch, Solar?
Can you restate his question?
The question was, what makes this different than the current open source projects such as Solar Cloud, which is the new version, Kata, and Elasticsearch. So the biggest difference I can point out is this was built with data processing in Hadoop in mind. So you could build these indexes and deliver them to Solar or to Elasticsearch from Hadoop, but I didn't want to change environments. I didn't want to have everything be built in Hadoop and then delivered to these other systems. I'd rather it be within the Hadoop ecosystem. All the indexes stored inside HDFS, so I have reliability. Kata, unless they've changed a lot of stuff recently, they allow for merging of indexes to get updates. But last time I looked, they didn't allow for incremental changes of those indexes through sort of a database like push, make this modification and make it available right now. So unless there's big changes that made in Kata, it hasn't had a major version change in probably a year.
Kata has the own problem because the Lucene 3.0 probably is not supported.
I'm sorry?
Lucene 3.0.
Yes.
Is not supported.
I'm using 3.4 in Blur, the latest release of Lucene. The Tata, you're saying that it doesn't support 3.0?
What about Elasticsearch? That's probably the closest.
I have less familiarity with Elasticsearch. It's kind of the newest on the block. I've been building this for about a year and a half, so it's hard for me to compare. But as far as I understand the way Elasticsearch works, it's almost like a gossips type of network where you emit your search and then it will forward it on to the correct indexes or shards. I'm really unfamiliar with it's able to scale to sort of the Hadoop way of hundreds of nodes. So that's what this is built for. So this is a standard data model in Blur, sort of in JSON form, to just kind of give a layout of what it is. Row IDs, arrays of records. Records have IDs themselves within the rows. Columns within the records, and basically those are your key value pairs or fields if you're talking Lucene code. So this is sort of a bubble approach to the same model, just to kind of show how it all sort of fits together. So the Blur architecture, all the search duties are performed with Lucene. There's no modifications in Lucene, there's nothing special to it. All the data is stored in HDFS only. There's no local replica copies of them. There's everything is built to run directly against HDFS. MapReduce is used to do all the bulk re-indexing, and incremental indexing is done through Thrift mutate calls. So it acts somewhat like a key value data store that you can mutate the data while it's live. Thrift is used for all the intercommunication, and ZooKeeper manages the state of the entire system and figures out what nodes are online, and so therefore what shards need to be brought up on what nodes. Blur uses two types of server processes, a controller process and a shard process. The shard process probably lives beside the data node Hadoop process in most installations, one for one. And the controller processes, you basically need to run as many of those as you would probably need concurrent searches. Because this is the thing that spreads out, sprays out the query and gathers all the results and gives a nice, clean, simple result to the client. So the overall architecture looks something like this. You can run as many controller servers as you like, as many shard servers as you need to store your data. If one shard server goes down, the shards that were on it are then automatically brought up on the remaining nodes evenly distributed. Because in search, if you need it to be a good response time, you can't have one node overloaded more than any other, or else the response times on that one may affect everything. So, as we all know, Lucene is really good for searching. It's a great library, so that's why I chose it. There's a big community. There's a lot of custom queries that have been written, a lot of features. It's got great adoption. As we were just discussing, there's several other projects that do open source Lucene as a distributed service. The API is very, very easy to extend and make into whatever you'd like. And the future of Lucene is looking good. Flexible indexing, a lot of performance improvements overall for fuzzy queries and various things. So the way the data looks in HDFS is just a standard directory structure with standard Lucene files stored on disk. Very simple, very straightforward. We write if the update, whenever the incremental updates come in, if they need to be persisted and we would like them to survive beyond failure, which most of the time you do, everything is issued to a write-ahead log, and sync is called on these write-ahead logs in HDFS, so it will survive a node failure. You can turn it off on mutates, so if you want to just do bulk inserts, let's say on a MapReduce job on a live table, you don't have to do write-ahead logs, because if the node dies, that MapReduce job will, those tasks will die and then readjust and fix the data. ZooKeeper keeps all metadata, all of the analyzer definitions, all of the state of the system, what nodes are online, what nodes have ever been online. who owns the locks for any given one of the writers of Lucene, and that way you can sort of figure out what's going on in the system. And that way, the shard servers don't actually have any intercommunication. They all rely on the ZooKeeper state to figure out what to do. Also, all of the online controllers are registered, so that way you can figure out what nodes are actually online that you can talk to. So our syntax is basically Lucene query syntax, except that there's a twist and you can sort of get an inner join between, if you're thinking in relational data, you can sort of get an inner join between column families. If you want to find any given row that contains messages that have Joe and Doe in the to field and contact name of Bill, this will find all those rows that contain that information. And those two records, those two documents, are actually stored as two different documents, and so it will actually do the inner join and return only the results that are the intersection. Beyond the Lucene standard query syntax, the API supports any standard blur, or any standard Lucene object queries. So if you're using a Java client, you can build up those queries any way you like, serialize them and send it in, and it will just execute it as is. So quickly, I'm going to go over the challenges, the technical challenges, the reasons why we built it, and sort of maybe what makes it unique. So the re-indexing of data, we needed to be able to re-index the entire corpus of data fairly regularly. So we wanted to do all the heavy lifting for us on the big cluster with all the processing power. So we built it with MapReduce, and we designed Blur to be able to run as multiple shard clusters. So not only can you shard out the data across all the HDFS nodes, you can have multiple clusters of HDFS nodes. So that way, when you're rebuilding the data and you're needing to land it on a system that's going to be turned on, you don't have a lot of I/O contention between the runtime system and the system that's being built to become the runtime system. So that way, performance of your users isn't impacted while you're doing this. The next big challenge we had was the random access writes with Lucene. So, as we all know, Hadoop provides a great file system. It's very robust. It allows for pins only, which is great for the way it's built. But the big problem is that you can't do random access writes during the write process. And Lucene requires that to be sort of native. The way you get around doing that is you can either write it locally to the local file system and then upon commit, upload it into HDFS. And we found that to be clumsy. We tried that first for a long time. So instead, this uses a layered file system approach. So every time a seek occurs, it actually writes a new block, metadata block location to the end of the file. And so it achieves the append-only writes in HDFS. However, it allows for the effect of seeks. So that way when the reads occur, it actually reads it the way Lucene would need to read it. This allows us to not have to modify Lucene API to prevent seeks from happening. There's actually a JIRA ticket in there asking them to do that for 3 or 4 years now, and they're reluctant to do it because they feel like they need the seeks during runs. So this gets around that problem. And the random access latency, that's really a big problem in HDFS. There's a lot of benefits coming in 3.2. There's a lot of changes being made. This will get hugely improved. However, during you're interacting with Lucene locally, it uses the file system cache in the OS to really fix the random access problems, because most accesses, because the index files are so hot on the local machines, are really fast by just default. And then they allow you to memory map those files to make them as fast as they can be on the machines. However, when you're interacting with HDFS, you can't get that operating system benefit, not without going over the wire every single time. So what we did was we built a off-heat cache, standard way you deal with this stuff in a least recently used map. So we allocate all of the upfront slabs of memory upfront as the process starts. And essentially replaces the operating system cache. But it doesn't adversely affect the GC pause times because it's off heat. And because of that, it allows us to achieve the performance levels of what a local Lucene installation would be. So the future, well, it's a new project. We just got it on GitHub a short time ago. I just cut a first release candidate, I believe, last week. So a lot of work needs to be done, but I believe we can make it more stable and we can make it better and faster. So future tasks are performance tuning tests, documentation. I'd like to have native GIS queries built in. Incremental updates from Hadoop, that's really just building the library so it makes it easy for the users to be able to create incremental updates as opposed to writing them by hand or pushing all of the updates to the controllers, which is not good. And native index splits. Right now you have to define how many shards you'd like up front, and it will spray all the shards across your cluster, but if your cluster gets bigger and you would like to split the data more, it won't do that without the full re-index. So in the future, I'd like to allow the users to be able to push a button and split all the indexes as they'd like, but do it in a performance way. So that's all I've got this evening. Anybody have any questions I can answer, or I'll be here afterwards. The question was, is there an API for optimizing the indexes? Are you talking about like a Lucene optimization? Okay. Right. So Lucene allows you to, optimize the index whenever you like. And from Lucene's perspective, everything that is normal about Lucene operates correctly in Blur. So you can call optimize on those indexes while it's running, and it'll optimize in place, which is optimizing on HDFS. So yes.
Okay. I just wanted to ask if what the intention of Blur is. Is it intended to be a competitor to Solar, or is it a different use case? And if it is intended to be similar or a competitor to Solar, how do you handle things like caching, facets, and things that Solar brings on top of this?
Okay, so facets are already supported in Blur. You can submit as many facets as you like with each query, and it'll give you back the corresponding counts that went with those facets when it runs. So that's already supported. As far as the competition with Solar, I would like to think that it's sort of a peer project, not a competition, because I want to be able to integrate tightly with Hadoop, with the Hadoop stack, and I believe Solar really wants to concentrate on being a web service wrapper around Lucene. They may end up solving the same problem depending on who is using them, but they're very feature rich. They want to do sorting, they want to do a lot of the GIS queries, they want to be able to have sort of anything be possible that's possible with Lucene. I'm reluctant to put in every feature. I want any feature I put in to be scalable. I want it to actually work at scale. So currently I don't allow for sorting at all because of the amount of memory it requires from Lucene. That may change in the future, but at this point it's not possible. So, does that answer your question? Any other questions?
So I'm assuming the NTR is not supported here.
Oh, absolutely, it is absolutely. Excuse me, the question was, is NTR, or near real-time indexing, supported? It absolutely is. So the Thrift API, once the indexes are built in mass in Hadoop, and they're delivered to a system, it becomes a read-write system. So you can call mutate, which allows you to delete, update, replace rows at will while it's running. And so the API allows the clients to decide whether or not a stale piece of data, so to get performance, it will allow, it will wait up to 1 minute to refresh those indexes and allow them to be shown. However, if the client needs an absolute response, they can force a refresh upon the query. So normally you typically have load incremental loads coming in sort of on the side, and your usage is coming in sort of from the top. And so the usage, if that is up to a minute old, it's usually not that big a deal. But if you're having pieces that need to do updates on the data, they need to see an absolute value of it at this time. So you're allowed to force the refresh or not, but it does it automatically.
Hi. Are you looking to integrate over here? Looking to integrate with the new HPadlog interfaces in 23 for separating, query searches from reindexing and others?
I haven't looked at any of that. I haven't, to be honest with you, I haven't looked at 23 other than the feature highlights of it. So that'll definitely be on my radar. Any other questions?
Who's your large user at this point of time? Implemented in a large scale?
I can't really discuss what my current customer is. It's big enough that I feel like if someone were to use it, that they would at least get off the ground and see that it works. So it doesn't really answer your question, but let's just say that it's in the dozens and dozens of servers is what's running on it. So probably a few hundred servers runs Blur across a few different clusters. So it's not running on only my laptop. Is that good? Okay. Thank you.
Thanks, Aaron. Our next speaker is Ronan Schwartz from Informatica. Ronan is a VP of Products in Informatica. He's going to talk to us about Informatica's HParser effort. This kid, oh, you're going to switch up. You're going to change up. So give us just 1 second there.
Hi everybody, thanks for having me here. Okay, so the hardest technical part will be about my laptop, but I was insisting on switching to my laptop, so I'll do a short demo of some of it. I'm here to talk to you about the HParser, and a lot of the use cases that I've seen out there are actually dealing with records, background use, and results. However, from my experience doing a lot of data integration and data processing, a lot of the records out there are actually not as simple and flat so that they could actually be easily going through a method reduce process. Some of the data out there is actually pretty complex, going in a variety of ways. There is hierarchy, structure, logic that kind of connects different parts and pieces of the data. The question is, how do you go between this blobs, unstructured data, semi-structured data, and so on, into something that could actually be processed in a scalable way? In many of the, Informatica is coming from the data integration background, which also requires you to do something extremely similar. Most of our customers are actually spending about 80% of their time just somehow scrambling the data, parsing the data, normalizing the data, so it can actually continue to be processed in a scalable way. HParser is actually based on Informatica technology for data and format transformation, with the sole goal, which is to take any format in any complexity easily in a visual environment and actually allow you to flatten it, to get it into the right record structure that you want, And basically with this announcement, HParser is working on Hadoop, basically is running on Hadoop, and I'll discuss and show how does it work exactly. The belief is that with focused technology on parsing, if you're dealing with data that has high complexity, you can reduce the time from spending 80% of the time on just breaking and understanding the data into something like 5% of the time. So what am I going to start, what am I going to demo? I'm going to try and demo actually how do you take a binary record or any complex record and really parse it and create from it this flat, simple record that could be then further processed. And what I'll show you is actually an Eclipse environment. How do you really do it with multiple records? Once you've done that, basically in a simple publish process, this is available for you as part of MapReduce. It's really, there is a simple call that just referring to that specific transformation. A blob goes in, flat records going out, ready to be used in the next step. Usually the problems that this is solving are complex flat files with hierarchy, logs that are not flat, XML, JSON data, that the deeper it goes, the more value you see. There is a lot of predefined content for industry standards. So Fix for the financial industry, ASN1 for telco are also, there are production customers that are using these formats on Hadoop. And a lot of binary documents, anywhere from PDF, Excel. So really HParser, what it, in a very single sentence, allows you to do is take this data and deal with it as if it was web logs, flat, delimited data. And instead of talking, I wanted to actually do a demo. And I hope everybody can see that. And what I'm going to do is actually start a project from scratch. So I'll show you what you can do if you're actually need to run a complex process on PDF purchase orders or something like that. So there are millions of purchase orders, all of them received in fax, in PDF files, and you actually want to process them for further analytics or anything like that. So besides giving my project a name, the next step that I need to do is really choose my desired output. Now I can import a comma-delimited file to show me this is how I want my output to look like. I can import an XSD or a JSON file. I can really import the structure that is my desired output. In this case, I'll go to my desktop and I'll pick up a schema. If you want to, you can actually define the schema also inside as part of inside the environment, which I won't do right now. Second. Real demo. The guy that's doing the demo is looking for the files. So I'm picking up a schema, and I'll show you the schema in a second. The next thing that's very unique with this environment, one of the hardest things to do is actually understand the data. It's much easier to understand the data if you can actually look into the data, read examples, see what is in there. So the next step that I'm going to do, which is optional, is really point into an example file. And this is where I have multiple examples to demonstrate. I'll start with a PDF example. You can see the file is automatically recognized as a PDF. You can support multiple languages in this PDF. And once I've done that, this is really where I'm starting to work with the file. This is a PDF binary file. I'm sorry, it will be hard to read that file from the last line, but it really represents company address, vendor, ship to, and then it got actually a lot of table data. In general, this data is very easy to read, and you can see how people can actually go and type it in. If you actually really want to parse this data, it actually is an interesting challenge. PDF is binary, the data actually don't look. It's all weird characters. But what is happening is that behind the scene, this is automatically translated into a textual representation, well formatted. At the bottom of the screen, you can actually see my schema. So this is the structure. And now you can really highlight the data that you want to extract.